Better? Okay. Okay, so before going to Kerr geodesics, one correction. I had written that for an orbit like this in Schwarzschild, T phi is equal to 2 TR. That's the wrong way around. It's TR is 2 T phi. So you do 2 complete azimuthal revolutions in the time that it takes to go 1 radial oscillation. Okay, so in Kerr are a little bit more complicated. The metric of Kerr in Boyer-Lindquist coordinates. So we've got a time piece, a radial piece, a polar angle piece, an azimuthal piece, and finally a piece associated with the fact that the space-time is rotating. So that's a T phi mixed piece. This quantity sigma is r squared plus a squared cos. Quantity delta is r squared minus 2m r plus a squared, and a is the spin angular momentum of the big black hole divided by its mass. Okay, 2 killing vectors here. The temporal one is just T component. The azimuthal one, which is just phi component. We have conserved mass and angular momentum. And Lz is U phi. Conserved quantities on geodesics. Then there's also a hidden symmetry which is not at all obvious, which is a killing tensor. K alpha beta is 2 sigma L alpha N beta R squared G alpha beta. These 2 vectors are ingoing and outgoing null vectors. L alpha is r squared plus a squared over delta 1 a over delta, and n alpha is r squared plus a squared over 2 sigma So L alpha is word null vector, and N alpha is an inward null vector. So in analogy, this equation for killing vector, K alpha satisfies a similar expression, which is the symmetrized derivative equal to 0. And we can check that K alpha beta, U alpha, U beta is constant. That's basically following exactly what you do for a killing vector. So I'm going to leave that as an exercise. To show this. So this constant is called the Carter constant. There's another quantity also called the Carter constant, which is, so let me call this capital C for Carter. There's another quantity that's capital C minus Lz minus AE all squared. So this is also a constant because C, Lz, and A are all constants. And this constant is also called the Carter constant. They're both called the Carter constant, even though they're two different quantities. So to get some feeling for what these quantities mean, you can take the limit to Schwarzschild. So the spin goes to 0. In that limit, C is the square of the total orbital angular momentum, and Q is the square of the piece of the orbital angular momentum that's out of the equatorial plane, or out of the pi equals 2, theta equals pi over 2 plane. We use these three constants of motion to get equations for t, r, theta, phi along the orbit. So we have that E is minus ut is minus gtt t dot minus g t phi dot, where here a dot means a derivative with respect to proper time. Lz is u phi, which is g phi t, t dot, plus g phi phi, phi dot. The card is kt t, t dot squared, plus 2 ktr, t dot r dot, plus all the other combinations. And we have that proper time is defined such that U alpha contracted with itself gives us S1. So that's another constant of motion. And this is GTT, T dot squared, plus 2 GT phi, T dot phi dot, plus GRR, R dot squared, plus G theta theta, theta dot squared, plus G phi phi, phi dot squared. So we now have 4 equations relating T dot, theta dot, and phi dot to these 4 constants of motion, E, Lz, C, and just this minus 1. So we can rearrange to get equations for each of these time derivatives. And when you do that, you get sigma T dot is E times R squared plus A squared all squared over delta minus A squared sine squared theta plus ALZ times 1 minus R squared plus A squared over delta. And let me define that whole thing to be Vt, which is a function of R and theta on the orbit. So it only depends on R and theta, not on T or phi. Then we have an equation for R dot, which I will write as sigma R dot all squared. And that is E R squared plus A squared minus ALZ all squared minus delta R squared plus LZ minus AE squared plus Q. And let me define it to be VR of R. So this only depends on R, even depend on theta. And I'm going to run out of room, so I'll move to the far board. Leave that. Okay, so 4 equations for theta dot. We have sigma theta dot squared. Theta LZ squared minus A squared cos squared theta 1 minus E squared, and define this to be V theta, which only depends on the polar angle on the orbit. And last we have Lz plus AE times R squared plus A squared over delta minus 1 minus A squared Lz over delta. And I'll define that to be V phi of R and theta. So one thing to notice, I've written all the derivatives in this form, sigma times dd tau acting on one of the coordinates on the orbit. So let me define this to be lambda. Is often called Mino time, although Carter introduced this time. Mino made extensive use of it more recently in the 2000s. So in terms of this Mino time, dr d lambda squared is Vr of R, d theta d lambda squared is V theta of theta, dt d lambda is Vt of R theta, and d phi d lambda is V phi of R theta. So the important thing to notice here is that the R and theta motion are decoupled. So you have your motion R is independent of your motion in theta and vice versa. And so up and down, and the two are not related to each other. So just like we did, we can write this oscillatory motion in terms of phase variables. So let's write the radial motion as R, the radial phase. R, just as we had in Schwarzschild. What is the meaning of Mino time? It's just a useful time parameter. There's no particular meaning. It's a time, it's special because it decouples theta motion. Otherwise, equation, you'd have a dependence on R in the sigma. So then the theta motion would depend on the R motion. Radial phase. We have the same kind of expressions for R max and R min that we had in Schwarzschild in terms of variables P and E. And they satisfy the equations VR of R max is 0, which is also VR of R min. So these are the two of the motion where dr d lambda is 0. And we for say theta is theta max times cosine of polar phase. And theta max satisfies V of theta plus or minus theta max is 0. So it oscillates from plus theta max up here to minus theta max down there. That's a little bit messed up. So if this is pi 2, then what we should have is cos max. And this is plus or minus cos theta max. So cos theta max is like the z, maximum z value, and minus cos theta max is down there. Okay, so we have r as a function of the radial phase. We have theta as a function of the polar phase. Then we need to find lambda as a theta. And we do that same way we found time as a function of, in the Schwarzschild case, d lambda d psi r is d lambda dr, dr d psi r. So d lambda dr is just 1 over square root of VR. With a plus or minus sign depending on whether you're going or inward. And dr by d psi r is right directly by taking the derivative of that function. So this gets you lambda as a function of psi. D lambda d psi theta so that gets us lambda theta and then last we need to find t and phi as functions of lambda. And you just find that from r of lambda and theta using so this gives us a complete description of the orbital motion. And as we had 2 periods or frequencies in Schwarzschild, we have 3. So we have period of radial motion, And this is the period as measured in Mino time. So that's integral of d lambda dr over 1 radial cycle, which we can write as dr over square root of Vr. Then we have period of polar motion, which is lambda theta is times integral from the bottom up to the top, or vice versa, over square root of v theta as a function of theta. So, well, let me write that more explicitly. So it is actually theta minimum at the top and theta maximum at the bottom. And you have one more period. So the period of the azimuthal motion is lambda phi equal to 0 to pi d phi over v phi. So again, just integral over one passage. Now, remember I mentioned over there that you can have resonances when two of the periods have there are two types of resonance. So that's phi resonance is n phi lambda phi, where these n's are positive integers. Then you have this so there you've got is n theta lambda theta. This have a very significant impact on the evolution of an orbit, because things that would be normally would normally be oscillatory in the dynamics. So you have e to the I n r lambda r frequencies here instead, n r omega r and theta omega theta times t. You'll have these kind of oscillatory functions in your dynamics that are oscillations of your radial phase and polar phase, but at a resonance, this is just one. For some combination of nr and n theta. if this equal to that, then you move that to the other side, and you'll have some combination that gives you 0. Yeah, so this has a significant impact, although I won't go into much detail on it. All right. So this is everything I wanted to say about geodesics. Any questions about this before I move on? Yep. In what sense? So mean of time is a variable along the orbit. No, this is just reparameterizing the orbit. Yeah. Yeah, it's not a coordinate. Okay, so that was all in geodesics. I now move on to how the orbits actually evolve when you take into account the self-force. So an important thing to note, the world line gamma and the metric perturbations Hn are coupled. However you incorporate the self-force into the evolution of the world line is also going to influence how you're going to calculate the metric perturbations. You can't do one without the other. So we'll outline several approaches in the literature. The first one I'll call Gralla-Wald. So Sam Gralla and Bob Wald, they're not the first to use this kind of framework, but they were the first to really treat it systematically for the self-force problem. So what they do is they take the coordinates on the orbit and expand that in a Taylor series. Where the different terms in this series have different geometrical interpretations. So say here's your big black hole, and here's your inspiraling orbit. The way this is written, you have, say, a geodesic orbit. Here I'm just drawing a circular orbit that is curve in space-time. Z1 and Z2 and so forth are actually vectors that live on the zeroth order geodesic and point towards, in some approximate way, the accelerated orbit. So this is a curve, and these are curve. So if you do a Taylor series, then you're also for the metric perturbation, or vice versa, is of the metric perturbation just writing the functional dependence, H1 is sourced by leading order G. And the second order perturbation depends on the leading order geodesic motion, but then also this correction, Z1. So then when you plug these expansions into you get a sequence of equations to solve. It's by equating coefficients of powers of epsilon. So you have the linearized Einstein tensor constructed for H1 is equal to 8 pi T1 alpha beta, which is the stress energy tensor of a point mass moving on the 0th order world line. Then you have the linearized to be dying here. Let's move it outside the pockets. Okay. This is 8 pi T2 alpha beta, which depends on Z0 and Z1. As I'll describe later, there actually isn't a well-defined T2 here, but just you can schematically think of it this way, that Z1 starts to source the second order perturbation, and then minus the second order Einstein tensor constructed from H1. And then if we imagine having an exact equation of motion, or an equation of motion for the exact world line, then when you substitute that expansion, you get a sequence of equations for Z0, Z1, and so forth. So the leading order equation is just the geodesic equation for Z0. Then you have an equation for Z1, where you have a force constructed from the first order metric perturbation. And later in the lecture series, I'll show you the explicit expressions for the self-force in terms of H1. And then you have a Riemann tensor term. Where this U0 is dZ0 d tau. So there's no Riemann term here. It appears here because when you expand one curve around another curve, then just the background curvature will influence how the one curve moves relative to the other curve. So just like if you expand two neighboring geodesics next to each other, you have this term being the geodesic deviation term that forces the geodesics to move away from each other. Here we're expanding an accelerated world line around a geodesic, so in addition to the geodesic deviation term, we also have the acceleration term. Now the trouble with this is, as you can see from this picture, Z1 is getting very, very big with time. So, eventually the accelerated world line plunges in, and you have a huge Z1 that is no longer a small perturbative quantity, it's a large quantity. So this, the setup breaks down with time. In particular, it's not valid on the radiation reaction time. Which, remember, was 1 over the mass ratio. So this picture is nice for deriving local results that are on a short time scale, but it doesn't apply over a long time scale. So let me move on to another way of treating the equations. Which I'll call self-consistent evolution. So this is the kind of picture that was used in the original derivations of the first order gravitational self-force. It was given the name self-consistent by Grella and Wald again, and then give you references here. This is Grella-Wald 08 and 2012. It's the first order result and the second order result. Then this was put on a kind of a systematic approach to perturbation theory in a bunch of my papers, 09, 12, and so this is first order, the second order, and a bunch of neighboring papers. The idea here is quite simple. You just don't expand the world line. You just treat it as a nonlinear function of epsilon. So then, to account for this, rather than using a strict Taylor series, you use a different asymptotic approximation. Where this H1 is now a functional of the accelerated world line, which depends on epsilon. So this depends on epsilon, and you don't have just a Taylor series. And then you have the same form at higher order. Now, when you have the metric perturbation in that form, you need to set up your Einstein equations a little bit differently. So remember I introduced this linearized operator. There was box, we put an H in here, was box H alpha beta plus 2R alpha mu beta nu. So this is the Einstein tensor, the linearized Einstein tensor in the Lorentz gauge. Yep. Yeah. So this is just a common thing to do in singular perturbation theory, it's called, where you don't have a Taylor series, you have coefficients of powers that themselves depend in some specified way on functions of epsilon. So I'll introduce a different expansion with the same idea next, but the dependence on gamma will be fixed by the equations I'm about to write down. So remember this, then we work in the Lorentz gauge, and H1 is the solution to the point particle equation, where now your point particle stress energy is not moving on Z0, it's moving on the accelerated world line. And the second order equation is similar, where you only have a dependence on the full world line, not on Z0. And you have this quadratic term constructed from H1. And then these equations are coupled to the equation of motion for Z, which is the equation that I keep writing down. Let me make the dependencies a bit more explicit now. So we have a first order self-force constructed from H1, which is the solution to this equation, and a second order self-force constructed from H1 and H2. And then in addition, there's the Lorentz gauge constraint. Which is a kind of complicated nonlinear constraint. So an important thing here is that this Lorentz gauge condition is applied the full metric perturbation, H1 plus H2, and so forth. It's not applied to each individual metric perturbation. So if you imposed it on each individual metric perturbation, then you'd actually just be going right back to the Gralla-Wald picture. So then you would have H1 exactly satisfying this equation, and you'd be forcing Z to just be equal to Z0. So these equations together automatically enforce this condition if you impose this condition on some initial time surface. So if you impose constraint here, and then you look in the future, the constraint is automatically still satisfied. So the idea of this is you're avoiding this expansion of Z around Z0. So rather than having this growing error, you're just directly following the accelerated motion into the big black hole. But this considerably changes the structure of the equations you're trying to solve. So if you go back to the Gralla-Wald case, what you do is you'd say, first solve the geodesic equation to pick out. You would then go up here and solve for the metric perturbation sourced by that geodesic. You would then go down here and find the correction Z1 that's generated by H1, and then you'd go back to the second order equation for H2. So it's a hierarchical structure. You solve one equation after the other. This setup doesn't have that hierarchical structure. These are just three coupled equations you need to solve simultaneously in some way. Now, if we're dealing with emeries, this still isn't quite optimal, because this doesn't say anything about what the orbit is actually doing in particular, whereas for an emery, we actually know quite a bit about how the orbit is behaving, and we can take advantage of that to come up with a slightly simpler, well, they look more complicated, but simpler in practice equations to solve. So that's called the 2-time scale approximation. And this was really pushed by Hinderer and Flanagan, although they only looked at half the problem, which was just the equation of motion, not the Einstein equation. This was in 2008. Sometime soon, there should be a paper coming out that's these two and myself and one of Aina's PhD students. But I'll just sketch how things work. So let's go back to the picture we had, where we had a set of constants of motion, E, Lz, and C. So those were only constants for a geodesic. But when we account for the self-force, we can still write things in terms of these quantities, but they start evolving slowly with time. So you can think energy and angular momentum are going out of the system, which is causing energy and angular momentum to slowly evolve. And you can't quite think of the Carter constant like that, but it's also slowly evolving due to the effect of the self-force. So these constants of motion are no longer constant, but they're evolving slowly. So we can write that as J alpha is some leading order piece as a function of T tilde, where T tilde is epsilon times T. This is called slow time. So it's slow because you need T to be of order 1 over epsilon in order for T tilde to be order 1. T has to change by a lot for T tilde to change by any significant amount. And then we'll have corrections to this. First order piece, and so forth to higher order. I'm brushing over a lot of details in how you get something that depends only on slow time, but I don't want to get too technical here. Then you have phases, which were that psi r phase I introduced, psi theta phase, and a psi phi phase. So this is just going to be phi on the orbit. Let me call that phi p. So it's the particles phi, not the coordinate phi in the whole space-time. So these are fast time variables. So the idea is we have these slowly evolving pseudo-constants of motion evolving in the slow time, and then we have these phases that evolve on the orbital timescale, which is much faster than the radiation reaction timescale. And they satisfy equations of this form. So the rate of change of a phase is defined to be some frequency And that frequency will have an expansion in terms of the slowly evolving constants of motion. So let me write down the next equation somewhere central because it's important. So if you integrate that equation, you get phases that are just the integral of the frequency. Well, let's convert this dt into dt tilde, which is 1 over dt, or sorry, 1 over epsilon times dt tilde. So then we have an overall 1 over epsilon and an integral of the 0th order frequency plus a correction coming from the 1st order frequency plus higher order pieces. So we can define this to be psi 0 of alpha and this to be psi 1 alpha. This is called adiabatic order. This is called post-adiabatic, or post-1 adiabatic. So adiabatic essentially means that you would be evolving slowly from one geodesic to another geodesic, the same way adiabatic would apply in thermodynamics. So you're slowly going from one stationary situation to another. Then post-adiabatic is the leading correction to that. So this expression for these phases also applies to the gravitational wave phase. And if you go through the mathematics of the expansion, what you find is this adiabatic bit depends only on the 1st order dissipative piece of the self-force. So the piece of the self-force that is responsible for changing constants of motion at leading order. The post-adiabatic piece depends on the conservative piece of the 1st order self-force. So to think about what conservative and dissipative pieces do, you can think of just a circular orbit, something like a drag force would be the dissipative piece, and then the conservative piece would be purely radial. So the conservative piece is changing the frequencies at fixed time. Like in a Newtonian situation, a radial force here would change the frequency as a function of radius. And then the dissipative piece is actually causing the time evolution of the frequencies. And this post-1 adiabatic piece of the phase also depends on the 2nd order dissipative piece of the force. So this is important because this equation is really how we estimate properly what we need to put into an Emery waveform, or an Emery model. So this piece up here is epsilon squared over epsilon, so that's order epsilon. So that's very small after a complete inspiral, so we can neglect that. But this piece here is epsilon over epsilon, which is just order 1. So after a complete inspiral, that could be 1 radian, it could be 10 radians, it could be 100 radians. It's independent of epsilon. So we need to keep that in our model to be accurate. And this tells us what that actually means. So in the first lecture, I did a very rough sketch showing that we needed a second order self-force. This tells us that we only need a certain piece of the second order self-force, which is the dissipative piece. Okay. Now, so far I've only discussed these expansions of the constants of motion and the phases on the orbit. So let me write that in a form more similar to what I did for the Gralewald and self-consistent expansions. We have Z alpha, the world line trajectory, being Z0 alpha. It's a function of the constants of motion, which depend on slow time, and all these phases. Then we have a correction, which depends on J0, J1, and the phases. And then you have higher order terms. Now, this looks kind of like a Gralewald expansion. I'm expanding the world line. But the form of the expansion is completely different. So this depends on the slowly evolving constants of motion, not on just a fixed geodesic constant of motion. And it depends on the exact phases of the evolving orbit. So this is not a geodesic. Unlike the Gralewald case, but the dependence of this function on J0 and psi is exactly the same dependence you have for a geodesic depending on a fixed J0 and a geodesically evolving psi. So this is the same function of J and psi as you would have for a geodesic, but it's not the same function of time because J0 is evolving with time now, and this is evolving with time in a different way than it would be for a geodesic. Is that clear to everybody? Okay. And the metric perturbation now has a form similar to this, where we've got a first order perturbation, depends on XA, where by XA I mean R theta phi, and this is the R theta phi on spacetime, not on the orbit, and it's a function of slow time. And then it has dependence on J0 and the phases. Second order, similar structure. Now it depends on J1 in addition to J0, and again depends on all the phases. Now, an important thing here is that Z0, Z1, H1, H2 are all periodic functions of these phases. that's part of the ansatz. So we can expand each of these functions in Fourier series. So Hn alpha beta is a sum over Fourier modes. Write that as n k alpha superscript alpha beta downstairs. And then you have phase factors coming from the orbital phases. So then when you come to solve the Einstein equations, you factor out all the phase dependence, and you only solve for the amplitudes. So I'll just write that down before we go for lunch. So the Einstein field equation becomes equations, a sequence of equations for those amplitudes. And I'm going to have to, unfortunately, add superscripts everywhere. Where the superscript means this first index tells you that there are no derivatives with respect to slow time. So think of a function like, or operation like partial derivative with respect to t, acting on one of these functions, where you had a dependence on slow time, and then you had phase factors. T tilde is epsilon t, so when a partial derivative with respect to t acts on that, you get epsilon times ddt tilde acting on the amplitude times the phase factor. And then you have the operation of this derivative on the phase factor itself. So that brings down a minus I k gamma dt times the phase factor. And this was omega 0 plus epsilon omega 1 and so forth. This is just the frequency. So when I write this 0, I'm excluding the order epsilon pieces in this expression. So I'm excluding derivatives, and I'm excluding corrections to the orbital frequency. So slow time derivative is set to 0, and omega 1 is set to 0, and all the higher order omegas. And the phase factor at the end always is just common to everything, so you can just factor it out of your equations. And we have 8 pi t alpha beta and I factored out the oscillator dependence, so these coefficients only depend on the leading order constants of motion on your accelerated orbit. So this is the first order equation. So that's an equation for these amplitudes. Then you have a similar second order equation for the second order amplitudes. But there's one new feature. So this 0 again means that I'm setting slow time derivatives and omega 1 to 0. And this quantity is just constructed from the amplitudes. But then there's one more term, which is the term in the linearized Einstein tensor that doesn't set these two things to 0. So it's the piece that's linear in slow time derivatives or linear in the first order correction to the frequency. So I'm going to put a 1 there, meaning just that. And this is again constructed from the first order amplitudes. So this means linear in slow time derivative and omega 1. I'll have to go over time just for 1 minute to write down the very last thing. Which is what happens to the equation of motion for the particle. That becomes a sequence of equations for these expanded bits of the constants of motion. So this capital F1 is constructed from that F1 and some other factors. And it's constructed purely from the amplitudes. It doesn't depend on the phase factors. And the subleading piece depends on an F2. Again, this is constructed from this F2, but part of it will also come from corrections to F1. But again, the key thing here is it only depends on the amplitudes, not on the phase factors. And at the end, you also have this equation for the phases as functions of the constants of motion. Okay, so how would you solve these equations? Well, you would pick some set of constants of motion, J0. You would then go to this equation and solve for the first order amplitudes. So step 1 is just pick your initial constants. Then step 2 is solve this equation for the first order amplitudes. Then you would know how J0 evolves, so that's step 3. And so you also need to pick an initial J1. So So these are just initial conditions. So then you go over here and solve for this at the initial time. Then you have the input to solve for the evolution of the constants of motion. And then finally, once you know the constants of motion as functions of time, you can reconstruct the phase at the end of the day. Everything before that is independent of the phases. All right, so I'm 5 minutes over time. Questions? No, okay. Tomorrow, I will go through a more concrete example of just doing the adiabatic order calculation. Just get the leading order evolution of the orbit. Thanks.
I mean, can you use the conservation of the energy momentum tensor to do the second step?
The step.
So
exactly. A lot of things end up being interrelated.
It still conserves the
leading order in the 2 timescale expansion, yes. Yeah.
Okay. Okay.
So what you find is that conservation of stress energy at leading order is equivalent to geodesic motion at leading order. Mm-hmm. Then this second order equation, conservation of this source, ends up being equivalent to having your self force. And also it plays into the slow evolution of the black holes, the big black holes, or mass and angular momentum. So there's some redundancy. Different parts of different equations contain the same information, and in practice that actually becomes an important consistency check to make sure that they both do really contain the same information.
Okay, let's go for lunch then.